Today we're going to learn what's more important than the fundamental theorem of calculus. What could be more important than the fundamental theorem, you might ask? How about a generalization of the theorem? We're going to call that generalization the fundamental theorem of line integrals. So here's the fundamental theorem of calculus, and just remember how important it was. This is one part of it. It comes in two parts. But the fundamental theorem of calculus said that if f of x is continuous on an interval ab, then the definite integral from a to b is equal to any antiderivative capital F at b minus any antiderivative capital F evaluated at a. Why was this so important? Remember, the definite integral is defined to be the limit of the sum of those rectangles. So you can calculate things like areas under exotic curves and so forth. And this said that in order to evaluate those areas, all you had to do was find any antiderivative, plug in the endpoints, and take the difference. And it didn't matter what the antiderivative was in the middle. You just took the antiderivative at the endpoints and subtracted them. Kind of a surprising result, right? But that was very powerful because it's exactly how we could evaluate these definite integrals, right? We didn't evaluate them by the limit of the sum definition. That was too hard. The fundamental theorem of calculus allowed us to evaluate definite integrals easily using antiderivatives for a wide variety of functions. So if we're going to generalize this, what is it we're going to do? Well, we need to sort of generalize our concept of the derivative. If you think of vector valued functions, that's what we've been doing lately, of more than one variable. This could be thought of as a vector valued function in one dimension. We just leave off the I because there's only one component anyway. And we could say the derivative, how do we generalize that to a function of more than one variable? Well, consider a vector valued function of two variables, and actually this applies to 3 variables or 4 or 5, and so you can have vector fields in any number of dimensions, right? If we have a vector field in the plane, it's easiest to write just 2 variables, right? F of xyi plus g of xyj. What should we think about when we think of its derivative in analogy to the fundamental theorem of calculus? We can think of the gradient, right? The gradient is the vector of partial derivatives. Maybe it has some special properties like the derivative did in first semester calculus. We'll say that just like a continuous function was important in the fundamental theorem of calculus because you can apply the theorem to that, we'll say this gradient will be important too. A vector valued function in the plane is conservative on an open plane region if on that region there's a function phi of xy such that f is the gradient of phi, an analogy to the f in the integrand being the derivative of some function called its antiderivative. So f is conservative if it's the gradient of some function on an open region. For instance, here's a function that's conservative, a vector valued function. E to the x cosine y I minus e to the x cosine y j, because we notice it's the gradient of e to the x cosine y, right? You take a partial, the gradient is the vector of partial derivatives. You take partial with respect to x and you get e to the x cosine y, that multiplies I. You take the partial with respect to y and you get minus e to the x sine y, and that multiplies j. So this is the vector of partial derivatives of this one, i.e. it's its gradient. Since this is the gradient of e to the x cosine y, we say this is the gradient of some function. This is a conservative vector field. Now, one thing I didn't mention in here, when a vector field is conservative, this function phi is called a potential for f. So that can be part of the definition too. Now, more generally, we might say, well, not only do we want to know f is conservative, let's see if we, to know it's conservative, we've got to find phi. How can we find phi? Well, we were just lucky here. Somebody told us this was a potential for this gradient. How can we actually check in general? Well, we could try this example here. Suppose I think this function is maybe conservative. How do I test? Well, if it's really conservative, then this has to be the partial of some function phi with respect to x, and this has to be the partial of the same function phi with respect to y, right? So we need to seek a function that has these partial derivatives. How can we find it? If you want a function that has a certain derivative, you take its antiderivative, right? So I can take antiderivative with respect to x and get the function, or I can take antiderivative with respect to y and get the function. It has to satisfy both, right? So by this first constraint, phi has to be equal, this is a partial derivative, phi has to be the partial integral of minus x over square root x squared plus y squared dx. Alright, and then also phi has to be equal to the partial integral of minus y over the square root of x squared plus y squared dy. Alright, so in order for phi to be a potential for a function that exists that has this gradient, we have to be able to satisfy both these equations. And if we can satisfy those, it's a conservative vector field, and if not, it's not. So let's see, how can we solve this integral here? Here's a hint. Alright, one of the tricks in integrating is if you see a substitution, like a function of a function, you think of letting u be the inside function. So let's try letting u equal x squared plus y squared. Furthermore, if you see a substitution leaves a derivative of that, or a multiple thereof, constant multiple thereof, multiplying dx, that's a good substitution usually. And that we have both cases here. If we let u equal x squared plus y squared, the function whose square root is being taken, then du is, we have to do, since it's a partial derivative, du dx, partial derivative with respect to u with dx, is 2x dx. But that's just about what we have. That being the case, we observe that dividing by minus a half, minus 2, minus a half du is equal to minus x dx that we see. So we replace the minus x dx with minus a half du, and we replace x squared plus y squared with u, and I'm sorry I wrote this wrong, this was cubed, copying it from here. And what this is now is the integral of u to the 3/2 on the bottom, minus a half du on the top, or minus a half the integral of u to the minus 3/2 du. And let's see, that's easy, right? U to the minus 3/2 is u to the minus 1/2 over minus a half. Plus an arbitrary constant. Well, the arbitrary constant in a partial integration, since y is being treated as a constant in here, is any function of y. So we'll say that plus there's any function h of y in here. And now the minus a halves cancel, and you see that in order for this to be the partial phi with respect to x, phi has to be equal to 1 over the square root x squared plus y squared, that's u to the minus 1/2, plus some function of y alone. Similarly, when we do this integral, so this is a substitution we made, we'll just put that on the side, let's interrupt here. We can also make it's the same substitution in here, except that du in this one is going to be du dy dy. Alright? And so now, if u equals x squared plus y squared again, du is 2y dy, just about what we have in the top here, and we can rewrite this just like the last one. It's minus 1/2 du over u to the 3/2 comes out to be minus a half u to the minus a half over minus a half plus an arbitrary function of x. We could call that k of x. Then 1/2 cancel. We say, oh look, we get the same thing. This is once again 1 over the square root x squared plus y squared plus some function of x. Now we can make these match, this one and this one, if and only if h of y and k of x are some constant, right? This one can depend only on y, this one can depend only on x. We can make these match if we declare these to be a constant. Hence we deduce, in this problem, that there is a potential, there is a function that has this gradient. It's any function of this form, 1 over the square root x squared plus y squared plus any constant you like, c. Since a potential function exists, we say this is a conservative vector field. If we can't make these match, then it's not conservative. It's actually unusual to make these match. You have to pick these just right. Most vector fields are not conservative. You just pick one randomly. And it's just like the in calculus 1, when you took an antiderivative, you got a particular function plus an arbitrary constant. Same thing here. When a potential exists, there will be an infinite number of choices, but they're all equal to within adding a constant, as you observe in this example. So there's how to tell if a vector field, such as a force field, is conservative or not. You can just integrate the components and see if you can come up with a function that works. Well, what's the big deal about that? It's an analogy to derivatives, so now we're looking, does that have an analogy in the fundamental theorem of calculus? Here was the fundamental theorem of calculus again. Here's the fundamental theorem of line integrals that corresponds to it. A vector field, now a vector valued function of two variables in the plane instead of a one component vector function of one function along a line. Suppose that this is conservative. It's the gradient of some function phi on an open region containing the points along the curve, and that the components here are continuous in this region. If C is any piecewise smooth parametric curve from one endpoint x0, y0 to another endpoint x1, y1 that lies entirely in the region, then the line integral that we've just been doing along that curve is equal to the potential at the final point minus the potential at the beginning point. Just like the fundamental theorem of calculus, you take the, except we call this a potential function, the potential at the final point minus the potential at the end point, and evaluate this line integral. What an easy way to evaluate line integrals if we just find the potential, and as you saw, it's not always so hard. Here's the other way of writing it. Some books like to write it this way. The line integral of the gradient of a function dot dr is that function evaluated at the final point minus the function evaluated at the initial point. The proof actually isn't so bad. Suppose I want to evaluate the line angle f dot dr where f is conservative. Because f is conservative, it has components d phi dx and d phi dy, right? So we evaluate this d phi dx plus d phi dy to evaluate the line integral. It's our theorem for evaluating line integrals. But now d phi dx is the same as d phi dx dt dt. Sorry, this was the way of rewriting line integrals, and this is our theorem for line integrals, that this can be evaluated by placing dx with dx dt dt and dy with dy dt dt and integrating t over the parametric path from A to B, t1 from A to B, to sweep out the curve. So we rewrite this notation and apply our theorem. And then, this is the chain rule, right? So this is ddt of phi. Well, the integral of the derivative, remember the fundamental theorem of calculus, if you have an integral of a continuous function, if ddt is continuous, like in the theorem, then you can take the function evaluated at b minus the function evaluated at a and take the difference, because now this is a function of one variable, t. You apply the fundamental theorem of calculus to generate this generalization of the fundamental theorem of calculus, that you just take phi at the final point minus the phi at the initial point, also written this way. So there's the proof of the fundamental theorem of line integrals. Now I like the way way your book has organized this material because they have boxed just the right stuff in here. What this says is the following interesting results. Both F and G are continuous in some open connected region D. That connected meaning it's not broken into pieces. You can take a path and get from any point in the region to any point in the region. So this is not connected. You can't take a path from here to here. But this one is connected. So if you have an open means you don't include the boundary. So if you have an open connected region D, then the following statements are equivalent. F is conservative on the region. The line integral around any closed path is 0. And the conclusion of the theorem we just did, that f dot dr is independent of path for every piecewise smooth curve in there. Here's the amazing thing about the theorem. Think about what it says for a second. If I have a conservative field, like gravity or something, you know, that second example we did was precisely the gravitational force. It's actually the inverse square law for gravity, if you think about it. And we found out that the gravitational potential was just 1 over square root x squared plus y squared. They sometimes write that as 1 over r was the potential for an object in a gravitational field, multiplied by a constant. But the theorem said this, that the line integral of a conservative vector field, f dot dr, along a curve C, a piecewise smooth curve with the gradient of f being continuous, was phi at the final point minus phi at the initial point. What does that imply? This says that if you take a line integral along a path here, C, and go from x0, y0 to x1, y1 of this field, this conservative field, you get a particular value. And if you take this path instead, you get the same value. As long as you go from the same point to the same point, it doesn't matter how you go. All paths to Rome have the same value for the line integral. So that's pretty amazing. It doesn't matter what path you take, as long as you go from here to there, the line integral has the same value. And another kind of stunning result, and this is actually major in the theory of gravity, is that if you take the line integral around any closed path, sometimes we write a little circle here to indicate the path begins where it ends. Similarly, for f conservative again, the line integral around any closed piecewise smooth path is 0. If you go from here and come back around to here, this line integral is 0. This is actually foundational in the theory of gravity. The idea is that this is the work you did, and if you go around a closed path on a planet and get back to where you started, then you have the same energy you did before because you've done no work. So the planet is able to continue in its orbit for hundreds of millions, billions of years because gravity is a conservative force. Same thing with the electromagnetic force. It's what keeps the electrons from spiraling into the nucleus, is that they have a conservative electric field, which is also 1 over r potential. All right, let's put the next slide up here. I hope. Alas, sometimes it's hard to do that integral, but find the potential. What can you do if you can't find the potential because the integral is too hard? Well, there is actually a theorem for that. Sometimes all you need to know is it's conservative. That way you know the thing isn't spiraling into the nucleus or whatever. The theorem says sometimes you can tell it's conservative whether or not you can actually find the potential. And here's how you test it. This is actually two directions. The first direction won't show that. If f and g, the components of a vector field, are continuous and have continuous first partial derivatives, which is usually the case for our calculations. Things don't just suddenly jump from here to here in a discontinuous way, instantaneously jumping. In fact, usually they don't suddenly have an impulse where they're not moving and suddenly they're moving fast, instantaneously they're moving fast, right? So this is the kind of case we have. If they have continuous first partial derivative on some open region D, and if the vector field is conservative, then it will be the case that df dy equals dg dx. You can look at a lot of functions and tell immediately they're not conservative because they don't have this property. So you can look at it and say, I don't need to try and find phi, it's not conservative by this theorem. Suppose you want to show that it is conservative. Well, it's a little more difficult because this isn't an if and only if statement, it's an if. What about the converse that says, should it be the case that if df dy equals dg dx, then it's conservative? Well, almost. The converse says if D is an open, simply connected region. Simply connected means that it has no holes in it, not even a point taken out in the middle. And that's actually very important. If there's no holes whatsoever in the open connected region, so that it's simply connected, and this holds, then it's conservative. So you just need that one stipulation that there's no holes in the middle of the region on which you're claiming it to be a conservative field. And then you can say the converse. That it's an if and only if. It's conservative on the region if and only if df dy equals dg dx in that case. Alright, we'll leave out the proof of that because we're really just interested in checking these out. Here's an interesting example in your book. A vector field f of x y equals y plus x plus y minus x, I plus y minus x. Yeah, I wonder if that's a conservative vector field. Well, let's just try this. You take partial of the first component with respect to y, that's 1. Partial of the second component with respect to x, that's minus 1. They're not equal, therefore it's not conservative. If it was conservative, these two would be equal. Here's another one. Suppose f is this function. 2xy cubed I plus 1 plus 3x squared y squared j. We could try and find by partial integration to see if this is conservative. Maybe we could do these integrals. They don't look too bad. But if we're not needing to find the potential, by the way, in physics, that potential is actually called potential energy, except they usually take it minus what we're calling. So they say that the force is minus the gradient of the potential, and so you see that minus sign different from what we're doing here. It's all the same, right? Let's see if this is a conservative field. We can check by our theorem there. If we're saying this is defined on the whole plane region, there's no holes in the whole plane region, so it's an if and only if statement. It will be conservative if and only if partial of this with respect to y is equal to partial of this with respect to x. So partial of this with respect to y is 2x times 3y squared is 6xy squared. Right? And then partial of this with respect to x is 0 plus 6xy squared. These two partial derivatives are both 6xy squared. Since they're equal, this is conservative. Even if we couldn't integrate it to find the potential, which actually we can do it same as the last problem. We would know it's conservative, hence the planet won't spiral in if it's under this kind of a force field, right? All right. Finally, where we go? We can extend this to more dimensions. There we go. We said we can do this more than in just plane regions. Suppose we have a vector field in 3 dimensions that has 3 components. All right, f of x, y, z is a function times I plus a function times j plus a function times k. When is it conservative? It follows the same kind of rules. It's conservative if and only if it's the gradient of some function of 3 variables, with the gradient being 3 partial derivatives. And in that case, on a simply connected open region, which is a little different, you can have a hole in the middle of it. Connected means that you can pull any closed curve continuously to a point in there. So actually you can have a hole in the middle of a region and it's still simply connected because you can kind of, you can have something like this. A sphere with a hole in it is actually simply connected in 3 dimensions, because if you have any closed loop in here, you can pull it around the hole inside and still close this to a point by moving it continuously. However, if you take a sphere and drill a hole clear through to the other side, now that's not simply connected, because you can take a string around the hole and you can't pull it continuously to a point. So the idea of simply connected changes a little bit, but it's the same theorem. On such a region, you have a similar test, and when it passes that test, you know it's conservative, it's a gradient of some potential, and you can evaluate the potential at the final point minus the potential at the initial point, and that will be the value of the line integral of a conservative vector field. So let's write that down there. Let's say similarly, f of x, y, z equals little f of x, y, z, I plus little g of x, y, z, j plus h of x, y, z, k is conservative is said to be conservative if f, a vector valued function, is the gradient of some function of 3 variables. In this case, on an open connected region, we have the same result, just in one more dimension. A conservative vector field, or the conservative f, satisfies curl of f equals 0. Remember the curl we just did briefly. So instead of saying dg dx equals df dy, we'll say if a field is conservative, then it satisfies dg dy equals df dx. In 3 dimensions, we'll say if a force is conservative, the curl of f vanishes. And actually, if you think about it, the 2-dimensional case, dg dx equals df dy is just the 3rd component of this. If you embed this 3-dimensional result in the plane, then you get the result we already had. It's a special case of this. And also, on a simply connected open region D in 3 space with the same things as before, piecewise smooth path, and if having first continuous. Alright, so my camera timed out in the middle of my lecture, but fortunately I saw it and didn't lose too much. We just have a little bit more to go. Here's the last part. Conversely, if the curl is equal to 0 on a simply connected open region in 3 space with f continuous and having continuous partials, then f is conservative. So curl equals 0 on a typical region means f is conservative. The converse holds within these kinds of regions. Well, let's do a couple examples so I don't leave you with so much theory at the end without another example. Suppose I want to show that this line integral, the book, by the way, writes these integrals f dot dr. Remember, the other notation is is a function times dx plus a function times dy. That's just another notation for integral f dot dr. One of the notations. We also have integral f dot TDS was another one. So there's all these things mean the same. Remember, when you see integral along C f dot dr, if you see the integral along C of f dot t ds, or if you see the integral of f dx plus g dy along C, these all mean the same thing. And now we're going to add another notation to it. When it's a conservative field, we might just put the endpoints because it's just not going to make a difference. But they'll use this to say, suppose you're considering some path C from this point to this point, we don't know what it is. Let's show that it actually doesn't matter what it is for this one because it's conservative, and then let's find its value using the fundamental theorem of line integrals. Then let's do it in 3 dimensions, the case we just mentioned. So don't let those notations confuse you. Make sure you look real smart at the end, just like calculus 1 when you called something the instantaneous rate of change. You also called it the derivative. You also called it the slope of the tangent line, or the velocity if it was derivative position. It was all the same thing. Same thing here. All right. So you can talk circles around the uninitiated now, right? Suppose I want to evaluate this. How do I know it's conservative? Well, I can either try the dg dx, dg dy, which is 3, is that equal to, I'm sorry, df dy is equal to 3, is that equal to dg dx, 3? Yes, it is. So we say if you call this little f and this little g, you notice that dg dx equals df dy verifies just by inspection that this is conservative. That means we'll be able to find a phi. So just like before, we take phi to be the partial integral of f with respect to x. And what does that give us? That we integrate, this is a constant because it's a partial integral, so it's 3xy is the integral of 3y with respect to x, plus an arbitrary function of y, right? And then we also infer by looking at it from this one that phi is equal to a partial integral of g with respect to y, oops, which just comes out to be 3xy plus an arbitrary function of x. And we can make these equal, right? If we just pick h of y equals k of x equal a constant, then we have a potential. We can pick any constant we want. So let's choose the constant. Right? The potential is all the same within a constant. We'll choose constant equals 0 just so we don't have to write so much. We'll say phi of xy is equal to 3xy. That's the potential for this conservative field. Right? The other way of writing this is equals f is 3y 3x dot dr. So if you read this as little f and this is little g, half the trouble in some of these problems is just figuring out the notation, right? So if we choose this one, we can add any constant to it, it's still a potential. And then the original line integral, oh boy, if I can leave room for this. This implies then that the line integral from 1, 2 to 4, 0 of 3y dx plus 3x dy is just equal to 3xy. Plug in the top end point 1, 0, 0. Not 1, 0, 0, 4, 0. Plug in the bottom end point 1, 2 and take the difference. Well, 3 times 4 times 0 is 0. 3 times 1 times 2 is 6. So 0 minus 6. The value of this line integral from this point to this point, no matter what path you take, is negative 6. That would be the work done in physics. This integral f dot dr, remember, is the work along a path. If this is actually a force field, 3y, 3x. All right. Or minus the work, since the work is minus the gradient of the potential, it would do 60 units of work in physics notation. All right. Now let's show in 3 dimensions that this is independent of path and find its value. How do we do this? On this one, it's harder to show. We have to show that the curl of f is equal to 0. And so sometimes it's not even worth trying this. It's just you want to try and integrate it and see what the function is. If I take the curl, then I've got I, J, K, right? And then the ddx, dy, ddz, and yz, xz, xy, the three components of the vector. Curl F means this, right? ddx, dy, the three-dimensional gradient, ddz, cross product with the vector F, that's your vector field, these three components. And so this is the cross product, goes to ijk, and then the gradient vector in the next one, the three components of F in the last row. And what do we get? I multiplies, we take this subdeterminant, ddx of xy is y, minus ddz of xz is x. And then let's see, this is dy, I just wrote that. dy of xy is x, minus ddz of xz is x, so it's x minus x. And then minus j, right, times the subdeterminant here, ddx of xy is y, minus ddz of yz, taking the subdeterminant, wiping out j's row and column, ddz of yz is y, and then plus k times, wipe out its row and column, take its subdeterminant, ddx of xz is z, dy of yz is z, and look, we get 0i plus 0j plus 0k, it's the zero vector. Sure enough, this is a conservative field, a little harder to check, but nonetheless there is this check. Now, what is its value? We can erase this top part since we're done with it. Let's find phi. Well, you can integrate each three of these. You have to integrate partial integral with respect to x, and you get treating y and z both as constants, you get x, y, z, plus an arbitrary function of both y and z, since they're treated as constants in here. And you do the same thing with these other two. You say phi of x, y, z, integrating the second component with respect to y. Right? If this is the partial derivative of phi with respect to y, then we do the partial integral, we get phi back. We integrate xz with respect to y. These are treated as constants, so that it's again x, y, z, plus an arbitrary function of x and z. And if you take phi to be, this to be the partial with respect to z, in order for it to be conservative, then we have to have the partial derivative of xy with respect to z is phi, well that's x, y, z again, plus an arbitrary function of x and y. And in order for phi to be all three of these things, these just have to be a constant. We conclude that we can choose phi to be the function x, y, z plus any constant. Let's choose it, the constant 0 just for simplicity. And now we know the value of this integral. The integral from 0, 0, 1 to 0, 1, 0 is just phi plug in the top endpoint, 0, 0, 1, minus phi, plug in the bottom endpoint, 0, 1, 0, and so we get 0 times 0 times 1 minus 0 times 1 times 0, we get nothing. This line integral along this path is 0. Thanks for listening. Try the homework and let me know if it has any problems.